this trial function or guess functions, when we substitute into this variational integrals and we minimize these variational integrals with respect to the coefficients. Okay, so we minimize the variational integrals with respect to these coefficients. So this is the coefficients. Basically, okay, we want to minimize this, okay, with respect to each of these coefficients, because we want to find the best value of this, the coefficients. Okay. The derivations, okay, is quite tedious. After minimizing this C, okay, sorry, is W, the approximate energy. So this is the approximate energy with respect to this coefficient. Okay, we end up with these simultaneous linear homogeneous equations. Okay, simultaneous linear homogeneous equations. So and each of these if we have here n basis functions, n number of basis function, this summation here over number of basis functions. Okay, so if n basis function, if we use here n basis function, we can get n simultaneous linear homogeneous equations. So this n simultaneous linear homogeneous equation with these C unknowns. Okay, this C n unknowns. Okay, so n numbers of unknowns coefficients. Okay, if you look here, okay, after minimizing this energy with respect to these coefficients, we can get these n simultaneous equations. Of course, we can find here, okay, n set, okay, n set of C. Okay, so you can see here n simultaneous equation with the C unknown of coefficients. Okay, we can get this n set of C. Okay, the coefficients. So there are two kind of solutions for this simultaneous equation, linear homogeneous equation. You learn in mathematics asas to solve this n simultaneous linear homogeneous equation. We say this equation is a homogeneous because, okay, at the right hand side of this equation, gx or the fx here is 0. Okay, so this is a linear, this is a homogeneous equations. Okay, so there are two kind of solutions. The first solutions when we set all the coefficient here to be 0. Okay, so this is a trivial solutions. Okay, when we set here all the coefficient here, okay, of course when we set here C1, C2, okay, up to this Cn, okay, you will get 0. So this all the coefficient here to be 0, okay, is one of the solutions of for these simultaneous equations. So when we set here all these coefficient to be 0, okay, of course these trial functions will be 0. Okay, so this trial solution, okay, is unacceptable solutions, because, okay, when we set all these coefficient to be 0, okay, the trial function will be 0. Okay, we get this trial function here to be 0. So we have a second kind of solutions, okay, the non-trivial solutions for these n simultaneous linear homogeneous equations, where the coefficient, the determinants, okay, the determinants of this coefficient, the determinant of this coefficient here, okay, equals 0. So if we have this n numbers of basis functions, this n number of basis function, we can get this n simultaneous equations with n unknowns of coefficients, and the non-trivial solution is the n by n here, circular equations, okay, these circular determinants, n by n circular determinants. Okay. If we can construct this n by n circular determinants, okay, we can find this n number of roots. So this is number of roots we want to, okay, we want to get this approximate energy, okay. So this n number of roots, okay. So how we define this matrix elements? So this is the matrix elements, okay. This is the Hamiltonian's matrix elements. This is the Hamiltonian's matrix elements, and S here, okay, is the overlap matrix elements, okay. This can be, okay, we can prove here, okay, the overlap matrix elements, okay, is given by this overlap of basis functions, okay. So if we have here two basis functions, okay, if we have here two basis functions, so if we write this C1 F1 plus C2 F2, okay, one of the overlap matrix element is 1, 1, okay, because two basis function, we can construct 2 by 2 circular determinants, okay. The non-trivial solutions, okay, is the 2 by 2 circular determinant, which is the solutions of two simultaneous equations, okay, when we minimize this energy, the approximate energy. So this is the energy. So this so the overlap matrix element here, okay, is 1. This is 1. The tau here, the volumes, the volume element here, okay, depends on the system, the coordinate system we use, okay. So the Hamiltonian's matrix elements, okay, this is the Hamiltonian's matrix elements for the 1, 1, okay. Of course, we can write here as I complex conjugate. So this is the Hamiltonian's operator given problem, okay. If the our problem here is the particles in one-dimensional bulk, the Hamiltonian here, okay, contains the kinetic energy operator plus the constant potentials, okay. This constant potential we can set, okay, as 0, okay. So the Hamiltonian's matrix elements, okay, will be like this, and you must know how to differentiate, okay, these matrix elements, okay, with these symbols, these notations. This is the operator, okay. We differentiate here this symbol H, okay, this capital H, the matrix element with the operator, okay, by this cat. Okay, this is symbol represent the operator. The ij here is the matrix elements. Okay, so you learn in physics. Okay, we can simply just write as f j or just jk. Okay, using the Dirac notations. Okay, so this is Dirac notations. Okay, other way we want to write for this Hamiltonian matrix element. Okay, we can write like this. Okay. Okay, for these integrals. Okay, for these integrals. This is for these integrals. Okay, now we obtain here the approximate energy. Okay, for the lower state, the next second lower state, and so on. Okay, we get here and lower state approximate energy. So each of these approximate energy, okay, from the variational principle states that the variational integrals, okay, which produce the approximate energy, okay, must be here greater or equals than the energy. So this from the variational theorems or variational principles, okay, the relationships between this approximate energy and the true energy. So this is the true energy. Okay. So this is the approximate energy. Okay. Okay. Now we are going to look, okay, two examples, okay, how this variables integrals actually works. On this basis functions given us this basis function f1, f2, and f3. Okay, we already here seen, okay, in our last lecture we use this one basis function. So this is one basis function. Okay, we prove that this approximate energy, okay, is greater than the actual energy. So we use this one basis functions. Okay, how about we include more basis functions in the trial functions? Okay. Okay, I have this new notes. Okay, I will upload in spectrums. Okay. Okay, let's say we want to use this one. Okay, we have here this F1 and this F2. Okay, okay, we previously we see, okay, okay, we seen this only the trial function here contains only one basis functions. Okay, we want to compare our results, okay, with these inclusions of second basis function. This is the second basis functions. Okay, we design this, and this basis function must be a well-behaved function, must satisfy the same boundary conditions, okay, for this particle in one-dimensional box. Okay, this example is for one particle in one-dimensional box. Okay, whereas these functions, okay, vanish at these two boundaries. Okay. And okay, as I said earlier, for these two basis function, the non-trivial solution here, okay, we can construct this 2 by 2. So 2 by 2. Okay, this is a non-trivial solution of what? Of these two simultaneous equation. These two simultaneous equation. Okay, yeah. I'm using this. Okay, this formula. Okay, this n simultaneous equation. Okay, for two basis function, we can get these two simultaneous equation. So this is the solution, the non-trivial solutions for the simultaneous equations. So when we substitute into the variation integrals, okay, we can get these two simultaneous equation with these two unknowns C1 and C2. Okay, we want to find the best value of this C. So the F1 here, so this is the F1. So the Hamiltonian matrix elements, okay, we define like this, okay. So this is the Hamiltonian matrix elements, this in Dirac notation, and this is in Dirac notations, okay. It's in Dirac notations. Okay, now we are going to evaluate, okay, each of these matrix element. We have this 2 by 2 circular determinants. Okay, we must find here 4 2 by 2 for Hamiltonian matrix element. This is okay, 4 Hamiltonian matrix elements. Okay, and also okay, 4 overlap matrix elements. Okay, this is the matrix elements. Okay, we must here evaluate each of these matrix elements. Okay, this is the matrix element. The evaluations of this 1H2, okay, 1H2, 2H1 here, okay, they are here, can get this same, okay, value for these matrix elements because we use real basis functions. So this is real basis functions. This is reals, okay. There is no imaginary number in this basis function. So of course, when we integrate here, okay, when we operate here, and this Hamiltonian operator, okay, containing this kinetic energy operator, okay, we here this Hamiltonian acting on this basis function, and then we multiply with this basis function F2, this acting on this F basis function, and then we multiply with this F1, okay, we will get this same, okay, value here. So these two matrix elements, okay, they are symmetry, okay, 1 2 2 1. So we'll get same value of this matrix element, and this as well for this overlap matrix element. We can prove this, okay, and then we substitute into this okay, each of these matrix element and overlap matrix element, we substitute into this circular determinant. solving this 2 by 2, okay, these 2 by 2 matrix elements, okay, I forgot one thing here. This sigma here, okay, this one. Okay, we set as each lambda n. Okay, we set here as is each lambda n. This is each lambda n. Okay, sorry, I forgot one things. Okay. One to 5, 1 to 0. Wait. Okay, so this value is for this value. Okay, right? So this h bar okay. So this Hamiltonian matrix element, this one. This is 1 6. This is how, okay, we rearrange this value, okay, in the circular determinants. Okay, so okay, so this suppose, okay, is a when we set this one, we substitute. Okay, okay, I will try to figure out this later. Basically, okay, I skip, okay, one of these calculations from here to here. Okay, we define here the sigma as something here. Okay, these equations. So now you can see here. Okay, I will fix these problems. Okay, this I will change this note. So you can see here. Okay, the value, the lowest value here. So we get here two value. Okay, so this one and this one. Okay, so the minimum value here is the lowest ground state energy. Okay, so this is the lowest ground state energy, 0.125002. Okay, we can compare with this exact value. Okay, we use one basis function. This is one basis function. okay, we get this 0.12665. Okay, we use this same basis function. So this is basis function. Okay, when we use this basis function, we get this 12665. Okay, you can compare this with this one. Okay, we get this significant improvement, okay, in lowering this ground state energy. Okay, 125002. Okay, close to this Z energy. Okay, so what we can conclude here, okay, when we increase this number of basis function from basis left meeting, why? Okay, the number of basis function, when we increase this number of basis function from 1 to 2 basis functions, okay, we here, okay, successfully lowering this energy significantly to this 1 to 5002, close to this exact energy. Okay, close to the exact energy. So when we can say, okay, if we are able to include these basis functions, okay, up to this infinite number of basis function, okay, theoretically we will get this true energy. Okay, if we are able to include this infinite number of basis function, okay, our calculation, the ground state, okay, energy will here equal to this exact energy 0.125. Okay, at the same time, okay, we get, okay, here the second energy, the second lowest energy. Okay, now we want to know, okay, what is the function here, the trial function here. Okay, phi 1 and phi 2 represent this state. The function is very important in quantum mechanics, the wave functions. Okay, in this case, our wave function here is the trial functions, the approximate wave function, because these trial functions will describe the properties of this state. Okay, beside the energy, one of the physical properties we here already determines, we can also determines other properties of this state, okay, through these wave functions. Okay, in these examples, the wave function here is our trial functions. So we know this trial function here has these coefficients C1 and C2. Okay, we must know what is this C1 and C2 in order to find the explicit form of these trial functions. And we also, okay, must find this C1, this second set of C1 and C2. Okay, let's say C bar 1 and C bar 2. Okay, to write this explicit form of this pi 2. Okay, so now we have this energy. Okay, we know the circular determinant is the solution of this 2 by 2 this two simultaneous equation here. Okay, we can solve this two simultaneous equation here, okay, if we know this E. Okay, we here already here obtain the first E and this second E. So the first E here, okay, which is our W actually, okay, this, okay, this is W, okay. we can write just to differentiate here with the actual energy, the exact energy. This is W. Okay, you can use different symbols you like just to differentiate this to, okay, E here with the exact energy. Okay, so this is E1. Okay, like in this note, this is actually this E, W2 and W. Okay, like this as, okay, like this one. Okay, this one W. Okay, so this is W. So now this W1 or E1 here, okay, we have here 0.125002. Okay, we have here 125002 each. Okay, each square m. Okay, we substitute into this equation. We substitute into this equation, this simultaneous equation. Okay, one of this approximate energy. Okay, when we substitute into this equation, okay, of course, we'll get this C1 and C2. Okay, how we do this? Here we can see when we use this first equation, this is from the first equation. Okay, you must follow this step. Okay, there are two steps involved here. If you want to evaluate this coefficient C1 and C2. Okay, the first step here, okay, we use this one of this simultaneous equation. Let's say we use this first of this two simultaneous equation, this one. Okay, we let this C1 here over C2. Okay, so we substitute this energy. So we can write this C2 in terms of C1, right? Here, this C2 in terms of C1 or C1 in terms of C2. Okay, so this is the ratio between this C1 and C2. So, so we have here this is C1 and C2. Okay. Now we have this pi. Okay. This is phi. The first phi we want to find. This one. Okay. This first phi we want to find here. Okay. C1 and C2 here. Okay. So this is the first step. Okay. We want to evaluate the C1 and C2. Apply this. Sorry, normalization constant. We apply these normalization conditions, okay, for these trial functions. Okay, when we normalize this, okay, this normalize this, we can assume this C1 now, this coefficient here going to be here, the normalization constant. This is normalization constant. So you learn in physical 1 and physical 2, when we normalize these functions, okay, we here equate this integral with 1. So we equate this with 1. Okay. This one. Okay. So you can see here, so this is the coefficients C1. So you can integrate here, okay, each of these terms, this one and this one, okay, we use the integration rules. Okay, you can see here we can integrate here. So the boundaries here, okay, okay, so we set here the boundaries here is from, okay, I will try to, okay, okay, change this node and include this, okay, assumptions where the distance here, okay, we set here from 0 to 1, okay, the L here is 1, okay, that's why we use this sigma. Okay, so the boundaries here, okay, the boundaries here is from 0 to 1. Okay, so you can use from the mathematical table integrals, these standard integrals. Okay, you also can use this one. Okay, just simply here refers to the mathematical tables of integrals. Okay, or you can integrate. You can actually using substitutions methods to solve these integrals. Okay, this integral, or just expanding this, okay, this, okay, cubic polynomial here, if you can expand this, okay, so you can solve this. Or you can refer mathematical integrals. Normally in exam, okay, I will use these standard integrals, okay, and then using these standard integrals, so you can find this C. What is this C? Okay, so when you get this C, okay, of course you will get this C2, because this C2 we write this in term of C1. You can write this in term of 1, so you can get this C2, this C2. Okay, we know this C1, okay, of course we'll get this C2. Now we can, okay, write this form for the pi 1. So this is the pi 1, phi 1, C1 and C2. Okay, you can see here for the ground state energy, okay, this basis function contributes the most, okay, to these trial functions. The coefficient here, okay, is larger than this coefficient C1, 4.9999, and so this is the best value we can obtain from these two basis functions, these two coefficients. So we can plot, okay, so the true wave functions, okay, you learn, so will be like this, okay, and you can compare this, okay, by plotting this function. So this function you can plot, okay, like this. So this is and the lower state here, so this is 1, this is 1, so the L here, okay, we set here to be 1 here, okay, 1 here, so this is 1. Now this is the ground state, okay. This function, more or less, this shape of this function, okay, like the true wave functions. Okay, you can also find the second, this, okay, you can plot for the seconds, okay, will be something like this, okay, the sine functions for this pi 2 when we use this second energy. Okay, we use this second approximate energy, we substitute into here, okay, you choose here the first equation here to find these two relations C1 and C2, this ratio, And then we use this second step for this. We normalize this, okay, phi 2, okay, phi 2, this phi 2, okay, we normalize this phi 2, so we will get this second set of C1 and C2. So we get this second set of C1 and C2, let's say C bar or C prime, okay. You can write this C2, phi 2, okay. So now we here can completely construct these energy diagrams, the approximate energy for this E1, okay, characterized by this state pi 1, E2 with this pi 2, okay. Now, okay, as I said, we can improve this energy here. We can include this is 1. Okay, we've seen this these 2 basis function. We can include this more basis function, this 3rd basis function and the 4th basis function here. Okay, using the symmetry properties of these functions. So this is the 3rd and the 4th. Okay, this all the matrix element here 1 3 2 1. Okay, we can show, okay, this they are symmetrics, they are symmetric here, okay, they are symmetrics. So this is the what call this odd functions, this is even, okay, so this is odd, okay, this is even, okay, sorry, this is this is even 1 2, this is 1 1 3 1 3 odd even, 1 4 1 4 1 4 1 4 2 3, sorry, this is 1 2 3, this is 1 2 2 4, this is odd, okay, this is even, okay, this is odd, okay. The overlap here of these functions, f1 and f3 here, okay. 1 here, this is even and odd, okay, we get odd functions. When we integrate here, we will be 0, and this is 1 4 1 4 here, this is even and this is odd, okay, we got odd functions, okay, integration of the odd function will give this 0, and then this 2, okay, as well, this even and odds here, okay. So using these symmetry properties for these functions, okay, we can simplify this matrix element. So now we get these 2 block diagonals, okay, of this matrix. This is first block diagonals. You learn in mathematics asas how to solve this block diagonals matrix, okay. So yours here, okay, the matrix elements, the Hamilton matrix element also you can evaluate here. So the block diagonal, you can see the all these off block matrix here, okay, is 0. So if the block diagonal matrix, so the solution we can write like this: the first block, so this is the second block, so will be something like this, okay. So this is how we solve these 2 blocks of matrix, okay, these determinants. So we can solve each of this block, okay. We actually have reduced this 4 by 4 matrix, okay, this 4 by 4 here to 2 by 2 here, okay. Two matrices with 2 blocks, 2 by 2 matrix, okay. This is 2 by 2 matrix, this is 2 by 2, okay, easily here can be here solved. And then one of this block here, okay, 2 by 2 matrix, So the non-trivial solution here, okay, actually this is the non-trivial solution for these simultaneous equations, and this is the non-trivial solution of these simultaneous equations. So you can see here we have this from these two simultaneous equation, so we can get this four set of C1, C1, C2, C3, and C4. Okay, so this is C1, C4. So we'll get this okay. So this is C4 double prime for this. Sorry. So this is C double prime 1. So this is C triple prime, okay, 1, okay, and so on. So we get these four sets of coefficients. So this is the from so the pi 1 here for n basis function, okay, we'll get this for trial function here, the wave function we want to get here, okay, with n four set of C1 and C2. Okay, you can see here, okay, you can see here, okay, the C1 this for this one, okay, the C3 here and C4 here is 0, right? This is C1, and this one, okay, the C1 and C2 here is 0. Okay, from these determinants, okay, and you can see here, okay, okay, C1 and C2, C3 and C4. Okay, so this is solutions determinant from here, simultaneous equation, this determinant from this solution of simultaneous equations. So we can evaluate this. Okay, I want to skip this one. Okay, this is one of the block diagonals. Okay, matrix. Okay, we get here. So this is the ground state energy. Okay, the next state. Okay, we got this four state and energy state. Okay, using four basis function. Okay, we'll get this four energy state here. Okay, with each here pi 1, pi 2, pi 3 with different value of coefficients. Okay, these coefficients. Okay, now you can see here, okay, we again, okay, have improved this. Okay, if we compare the ground state here, 1, 2, 5, 0, 0, 1, 8, okay, compared to here, okay, 0.125002. Okay, when we use four basis function, okay, we get here, okay, 0.2150018. Okay, again, we have here improved the ground state energy. Okay, okay, at the same time also we have improved this second energy. So the second energy here is 4.93487. Here we have improved here. Okay, this one. This one. 0.5 493. Okay. Uh, 0.4493. Okay. Four nine. Four nine, 49, 49, 49, 49. Okay. So the lowest energy here, okay, is this one. Okay. From 49, okay, we can improve, we improve here, okay, lots here, okay, from 49 to 12934. Okay, so this is the second energy. So from here, okay, you can see 4.9234, okay, to this energy. So this is the second energy. Okay, improve a lot here for this second energy. Okay, so now we have here proof by here increasing the number of basis function, we have reduced very significantly this approximate energy. Okay, this approximate energy. Okay, so this is each of the trial function. Okay, this when we use this approximate energy, we substitute into simultaneous equation, this simultaneous equation, this simultaneous equation. Okay, we will obtain this. Okay, and this W. So this is the second W. This is third W, and this is the fourth W. Okay, into the simultaneous equation. Okay, so the trial function also, okay, in modern quantum chemistry, or computational chemistry, this linear trial function here, this is summation here, okay, over here numbers of basis function. Okay, we can include here the variational parameters. Okay, so this is the variational parameters. Okay, in order to improve our calculation in modern quantum chemistry. So this alpha is the difference, and we can simultaneously optimize these parameters, this coefficient C, and this variational parameter alpha. Also, this is the variational parameters. You also you can refer the you can do the tutorials. Okay, how we optimize the variational parameters. Okay, so that you can get the best value of alpha. Okay, once you get the best value of alpha, you will get the best value of this minimized energy. Okay, what is the minimized energy? So this in examples, okay, the hydrogen atom here using the trial functions. Okay, okay, you can refer your notes. Okay, physical 1, physical 2. This actually likes the true ground state energy, with the Z, the atomic number here. Okay, so the alpha here actually the effective nuclear charge or atomic number here. Okay, so we want to get this alpha. Okay, so the linear combination, the number here you can see here. Okay, we increase from 1 to 10 to 16. Okay, to 16 here. Okay, whereas here the coefficient here, okay, treated here simultaneously, okay, minimizing this two, okay, variation integrals and coefficients. So we treat here also this coefficient as variational parameters, okay. So this coefficient also, okay, we can treat as variational parameters because we here treated simultaneously this optimizing this to C and alpha, okay. So this is how the energy here, okay, improve from 424 to 499, okay. So the energy here going down here, okay, the energy from 424 to 499. So what I can conclude here, in modern quantum chemistry or quantum computational chemistry, use in modern quantum chemistry use this basis function, these Gaussian type functions GTO for atomics or molecular calculations. So to find the best forms of trial functions, okay, in quantum mechanics, the trial function, okay, is actually everything's to describe the molecules and atoms, because these trial functions or the wave functions or the orbitals, okay, we can use to define to find, okay, beside the energy, the other physical quantities like dipole moments, okay, the positions or of the electrons or molecules or atoms, okay, by squaring of this trial function. And also you can also the transition of a moment is very important, okay, if you want to determine whether the transitions is allowed or is allowed, okay, or forbidden, and to find this, okay, all these quantities you must find, okay, the best form of these orbitals or trial functions. So now, okay, we can stop now, okay. Next week, okay, we will continue with perturbations, okay, this variational treatment for the ground state of helium, okay. For heliums, the simplest. So this is a good models, okay, to describe for the interacting electrons, atoms, okay. Helium here we know containing 2 electrons, so you can, okay, try to look this, okay, calculations, how we can use these trial functions, okay. This trial function here, so this is trial function from the pi 1, this orbital approximation 1 and second electron. So this is a second electron here. So this is first electron, this is the second electron here. As a function here, we labels here, okay, as electron 1, electron 2. And this is orbitals for the ground state here. So we use this 1s orbitals. So this is 1s. This is